Infrared spectroscopy is a powerful and convenient characterization technique with wide applications. It provides us with information about the types of bond present, and hence the functional group within a compound.
Infrared radiation is an electromagnetic wave with wavelength ranging from 700 nanometers to 1 millimeter. A quantum of electromagnetic radiation is also referred to as a photon. The energy of a photon can be described by E equals to h nu, where E is energy, h is the Planck constant, and nu is the frequency. Alternatively, E equals to hc over lambda, where c is the speed of light in vacuum and lambda is the wavelength. The wave number of a monochromatic light beam is the inverse of its wavelength, where wave number equals to 1 over the wavelength. In infrared spectroscopy, the wave number is measured in inverse centimeters. With the previous equations, the energy of the photon can be expressed as E equals to hc times the wave number. Energy can be observed to be directly proportional to the wave number. Therefore, wave number is used as it offers more accessible values for IR spectroscopy as compared to using the real value.
When infrared radiation is shown on a compound, the incoming photons interact with electrons in covalent bonds and excites the bond from ground vibrational state to first excited vibrational state. These characteristic vibrations allow us to determine what bonds are present in the compound. The IR spectrum is generally plotted as percentage transmission against frequency. When the sample absorbs infrared light at a specific frequency, transmission decreases and hence we see a peak hanging down from the top of the diagram. The shape and frequency of this peak will help us find out which bond is causing the vibration.
After learning about how energy is affected when infrared radiation is absorbed by the bond, what does this mean in the physical world? The physical interpretation of this is the vibration of bonds. Consider a system of two atoms joined together by a bond. They can vibrate by symmetric stretching or asymmetric stretching. They can also vibrate by bending, rocking, wagging, and twisting when excited by infrared light. However, do take note that only bonds or compounds that have a net dipole moment are detectable by infrared spectroscopy. Dipole moments are present when a less electronegative atom is bonded to a more electronegative atom. For example, the carbonyl bond C double bond O has a large dipole moment. Likewise, a compound has a net dipole moment if individual dipole moments of the bonds present do not cancel each other out. For example, even though water, H2O, has two similar OH bonds, it has a net dipole moment as the individual OH dipole moments do not cancel each other out in vector form. However, methane, CH4, is not detectable by IR as the dipole moments due to the 4 CH bonds cancel each other out.
Intuitively, stronger bonds need more energy to vibrate. Thus, infrared light of higher frequencies need to be absorbed. This is why triple bonds vibrate at higher frequencies than double bonds, which vibrate at higher frequencies than single bonds. Likewise, bonds that are more polar, i.e. have a larger dipole moment, are stronger than less polar bonds, hence vibrate at a higher frequency. Thus, it is very easy to spot such bonds as their peaks are sharp, intense, and occur at relatively high frequencies. With all of these useful tips, you are now all set to embark on your journey of unlocking the secrets of chemical compounds using infrared spectroscopy.